Good morning and welcome to Thursday. I'm very excited about today. We got a full day, and every year of EVCON, I have planned a Thursday evening barbecue at my house, and it's rained every single year. And today we have 0% chance of precipitation, and so that's going to happen. I've got a special guest this afternoon. I don't even know the guy, but he's Craig Smith, and he's supposed to be a car hacking expert. And Colin and John are going to kick off the morning, I think, with some battery love and some can stuff. And so John has spoken at virtually every EVCON, so for most of you he needs no introduction. For the rest, he is the author of a book called Ice Free. He's converted a Honda Civic to battery electric car, and I think his family driver is an Ampera, and he kind of opened my eyes to what the Chevy Volt thing was really about. And so that's been an interesting thing. But John and I have collaborated on passing each other mostly unreadable papers back and forth from universities and stuff about batteries for 4 or 5 years, and we've each done some battery testing. I've kind of I feel like I've graduated from that. I don't look at a lot of batteries anymore up in the lab. Probably have to get back into that as we go into some newer chemistries, but John has pursued it from a fairly rude garden shed setup to ever more advanced testing, and we've actually provided him some batteries along the way, and he's done some of the more persistent tests. I'll run it 10 times, he runs them 800. And that's what it takes to find out what's really going on. He is from Surrey?
No, Worcestershire.
Worcestershire.
Like the sauce.
I never get this right.
Yeah, you always get Reading and Redditch confused.
Worcestershire. And Avon on something. Stratford on Avon. It's somewhere in the United Kingdom.
That'll do.
And so we can all give a warm welcome to our ongoing, sort of almost on-staff speaker for electric vehicle conversion conventions, John Hardy.
Well, thanks so much, folks. See if I can flip this on. Oh, yeah, what happened? Let me put it on pause.
I want to hear you say the jingle age show, baby.
The what?
It's not Australia.
I know, but
He was all set up, I think.
I was all set up. Oh, hang on. That's the simplest.
John believes in preparing for speaking engagements. I don't know what that's about. Yeah.
Well, very good to be here, folks. Awfully nice to see all your smiling faces again. I've been at every EVCON apart from the very first one, and Jack's been very kind in his comments. I have to say Jack got me pointed in what I think is probably the right direction when everybody else was pointing the other way. So I have a great debt of gratitude to you, Jack, for that, and I'm most grateful. As you said, well, there's at least one of the tests he provided the cells for, which was nice. This is what I'd like to talk about today. I'm just going to, for those of you who haven't heard me yammering on before, I'm just going to briefly cover some of the earlier testing that I did, that is before this year. Then last sort of 12 months or so, I've been doing a lot of testing on different chemistries using 18650 cells, the small sort of grown-up AA's size cell. And I've been testing a number of different chemistries just to see how they behave compared with what we observe with the lithium iron phosphate. Can you guys hear me all right at the back? Good. Then I'm going to show you some cell failure examples, some examples where we've actually caught cells failing during the test process, because it's the failures that will, I suspect, get you. Just going to show you some very odd stuff about self-discharge. One of the things that's gradually dawning on me, looking at some of this stuff, is how much we just simply don't know about the way these things behave. It may very well be that folk here have observed stuff that nobody's ever really captured, so feel free to chip in if you have an observation. I'm also going to talk about, very briefly, about the Civic, that we're converted, but we're planning to use it as a test bed as well. In other words, rather than just as a daily driver, we want to get some data off the batteries to observe what's happening. And then I'm going to talk briefly about some of the plans that we've got for future testing. So we start with the sort of earlier testing. This was the first lot of testing I did. I got some headway cells. These are lithium iron phosphate, 10 ampere hour cylindrical cells, and that test I managed to get them through about 600 cycles, and then one of the cells failed. That was really sort of a little bit of a sort of way moment, because we checked for what we were looking for was cell drift, because at that time everybody was saying you must have active balancing because these cells drift, and it was clear that they didn't. And that was the first numerical data that we had. It was also the first chance that we had to take a look at the sort of dynamic behavior of the cells, because the world just seemed to assume, and to some extent still assumes, that you can use the voltage of the cell as a surrogate or an indicator of its state of charge, and that's only partially true. You've got internal impedance, you know, a sort of voltage change that goes away when the current stops, but then you've got processes going on inside the cell, which means the voltage changes even when the cell's sitting there open circuit. I'll be showing you a graph a bit later on where you can still detect that change a couple of months after the cell's gone open circuit. So there's a lot going on that's not terribly well understood. Then I did a second test where I was trying out some of the, I don't know if those of you who've been in the game a bit longer will remember the sort of shunt balancers that were being sold a few years ago. I made a cobblers of designing the test, really, and I managed to destroy the pack in under 100 cycles. Then I got some Carl 40 Fi cells, same chemistry as the one that Jack's been selling for some years, and did 2,000 cycles with those. And again, there was just no cell drift. There was no problem at all. And then did a fast charge test, again Cal 40 FIs, and I was charging these at 3C, about 120 amps. And again, I don't think the results could be described or defended as statistically significant, but certainly there was no visible sort of drift in the cells. Slightly faster aging. I reported all of that last year, and I think there's something up on my YouTube channel about the results from that. But if you're interested, by all means grab me.
Basically, they're about the same scale as we talked about with the Idaho National testing last week on these cells.
Yes, yes. So
It does accelerate the aging, but you need test equipment to detect it.
So all of that earlier testing, we used the static bottom balancing before assembly, and no active balancing during the process. During that, we didn't start with it, but during that we started with, we developed a process of screening the cells, where effectively what I've got now is a couple of automated rigs to bottom balance the cells. And then having bottom balanced them, I just leave them sit for a week. and monitor the voltage. And what I'm looking for is anywhere there's any significant self-discharge, because it seems like there's a small percentage of cells that have what's sometimes referred to as an internal soft short, and their rate of discharge will be slightly higher, and you want to get rid of those. The other thing that I did was I used voltage followers based on operational amplifiers. Again, an idea, to be fair, I pinched from you, Jack. You put something up about this some years ago. Used voltage followers based on operational amplifiers. If you could imagine, if you've got a 100-cell pack and you're monitoring the voltage of each cell, you've got a little cell tapping, you know, a wire that leads to the top of each cell. If you're taking a milliamp out of each of those tappings, the difference in drain between the bottom cell and the top cell is going to be 0.1 of an amp. So it's really important, if you're doing any voltage monitoring on a battery as opposed to an individual cell, to make sure that your cell voltage monitoring system isn't distorting your results. I've been looking in vain for years for any statistical data on cell drift in batteries, and I eventually found something that was done by NASA some years ago, and you could actually see from the graphs that they published that they had actually got precisely this problem. They'd got an equal linear difference between each of the cells, and so that's a very important thing if you're doing cell monitoring.
Could I add something to that, John? We attempted a EVTV PMS with Ed Clausen, and I sketched out a thing that I stole from a Tesla patent of how to basically do what John's done. And he took that to, I bet, 15 different authorities who each explained to him what was wrong with it and came back with the same ladder diagram that everybody uses to tap cells. And I explained to him 15 times why we weren't going to do that.
Yes.
And walked him through the whole process of why the top cell wound up drained more than the bottom, or the bottom cell got drained more than the top cell. And he said he understood every time, and a week later would come back with another authority to quote of the same circuit turned sideways. And then the next week it'd be an upside down version of exactly the same circuit. There's only one circuit used in all of electronics for batteries to measure individual cells. And everybody thinks it's original, and they draw it slightly different way, orientation, but it's the same ladder every time. And I had a thing where we would switch in a cell to a cap, and then disconnect it, and then pass that cap into an analog digital converter, and then take the next cell and sort of switch them in series. It was a little complicated, and so Ed wanted to simplify it, and he kept going and finding authorities to explain to me why what I was wanting to do was not the thing to do. We've never gotten the BMS actually working. I think Colin and he have one version finally that sort of works. And I did take his design and send it to China and have 5 boards made, and then he told me he had another error in the board. So I've got 5 erroneous boards, but that's what happened to the EVTV BMS. I've never been able to sell the concept that John is describing to you. You're causing the cells to drift by measuring them. And there is a way around that, but it's a little convoluted. John's solution is an operational amplifier that, in theory, ideal op amp has infinite input impedance and 0 output impedance. None of them achieve that at the ideal, but it's very high. You're drawing nanoamps from a $2 op amp, and that's what he did. I didn't mean to interrupt.
Typically 20 meg ohms.
Right. Yeah, 20 meg ohms.
I'm not quite sure where to stand to avoid the feedback here. As we've been talking about it, this is a cell board I've got at home. Jack assured me yesterday it wouldn't work, so I may need to go back to square one. But basically what this contains is an Arduino something Pro, little tiny board clone, which is the intelligence, and then there's an isolation amplifier on here. So that what this is intended to do, and I know one on its own works, but I don't know whether it will with the whole lot, is to put voltages and temperatures onto an I2C bus, so that I can read off the temperatures and voltages of each cell. Shall I just pass that round, Michael? So that's our sort of first go at a cell board for putting in the Civic. And again, I'm grateful to various folk here for pointing me in the right direction. I was picking various brains last year about this device called Eagle, which I've not come across before. So, anyway, back to things. The conclusions we had from that first lot of testing was that we just couldn't find any discernible drift in lithium iron phosphate cells. What Jack had been saying all along, and what the EV community had been pasting them for, Jack was absolutely right. There just was no drift with healthy cells. The other thing was that we found that the whole pack battery life was comparable with the advertised battery life for the cells. That was and that was kind of encouraging. This really is the sort of principle we're using. We should perhaps have put this up at the beginning, but basically what we've got is a charger and a load, and then software that flicks a switch between the two so that the thing just sort of sits there. 1 year I left one of these running while I was at EVCON, but I decided to shut down the test before I left this time. And this is really the sort of proof of the pudding, if you like. This was the discharge curve from cycle number 2000 of the CALB pack. And it's the whole discharge curve, and you can see that they're all going over the knee together. I mean, that's that's what you really want, is that they're all sort of pretty much together, and they you know, if you got down to there, the battery voltage would have dropped to the point it would be pretty obvious you were out of power.
John, what's the time scale along the bottom axis?
Sorry.
Cycle.
This is just this is the discharge curve. So this is the voltage.
Yeah.
The thing's connected up to a resistor. So this is the time. So this one started at 2:24 in the morning,
Yeah.
and that discharge finished at 4:48. Does that make sense?
Oh, it's cycle number 2000, not the entire life
Cycle number
of the
2000,
pack.
yes.
Okay.
Yes.
Yeah.
So yes, this is the discharge curve for the 2000th cycle.
Got it.
That's awesome.
So bottom balance at the beginning never touched again.
Precisely.
And 2,000 cycles later,
Yes,
there
yes.
they are.
Four different runs.
Sorry?
4 complete different runs, because you've got 4
No, that's
lines.
four
That's
cells.
four
So
cells.
there's-
Oh, these are the
there's-
4
there's
cells.
actually
Okay, 4
8
cells.
cells.
Or 8 cells.
Yes, 8 cells, that test. And they're all going over together. If anybody wants the data from that, send me an email.
You can't beat it, John.
Sorry?
You can't beat it, it's just what you want.
Precisely that, that's exactly what you want.
Were those Cal CA40?
Those were the CALB CA40s, yes. I've reported on those tests in previous ones. There's some interesting issues about overcharging, about over voltage on charging. Jack actually referred to it yesterday. what we found during the process of charging, across the whole cycle, you'd get they'd all be together pretty much on both the charge and the rests and the discharges. They'd all just track each other a bit like that one. But there was the one point where they would tend to diverge was during the sort of constant voltage phase. If you've got constant current, constant voltage phase, then they would tend to diverge. The headways were worse. They just went all over the place. That was the bundle of snakes. But even this pack of CALB CA40 cells, there was one cell which tended to diverge. You know, it got to 3.7, 3.8, while its contemporaries were down around 3.6. So, you know, the voltages tended to diverge. So I would strongly suggest that you actually, if you can, you cut off charge relatively early. Don't go for that last, you know,
Half block of range.
half watt exactly. You know, I mean, the way I got mine set up, I think on the Civic I got up to about 3.55 volts per cell nominal, and then I just cut the charger off at the knees. I've got the thing wired through the JLD 404 relay. So when the JLD 404 says 3.55 volts per cell, you know, whatever the multiplier is, it just opens the relay and disables the charger.
Something that we did when we were assembling the pack, sorry to interrupt, but something that we did while we were assembling the pack for Ray's Miata was we sat there and watched on the very first charge, and we're probing every cell, watching for Napoleon, as we termed it, the one cell that would start rising in voltage ahead of the rest.
Yep.
And we cut off charge at 3.6 when he hit 3.6, I want to say. Everyone else was still chilling out around 3.5, 3.55, but that one started going up. Like, all right, well that's the point we're going to hit. Coincidentally, 80 cell pack, it landed at what, 3.55 average. So yeah, you take the cells times 3.55, and that correlated with our experience.
Yes.
It's not terribly critical. You can have a lower capacity cell go up to 3.8 or 3.9. You haven't heard anything. There's no damage to the cell occurs until you're well above 4.2 volts. So when you're charging to 3.6 and have one that hits 3.9, nothing bad happens.
No.
But what I will relate is in the interim, while we've been doing all this over 6 years, all the OEM cars undercharge their batteries. And that's because whatever their theory is, they do have to do that, comply with the California 8-year, 100,000-mile warranty. And their strategy for not having to pay anything on that is to undercharge their pack. And so you're not required by law to fully charge these cells ever. They're not like lead acid cells, where if you don't do that, it's a problem. But lithium-ion cells, if you could charge them to 51% and discharge for 49%, they'd last 300 years.
Are the OEMs undercharging by measuring voltage or counting amperage?
By measuring voltage.
Right. Where were we? Jack, what time are we knocking off here?
When you get done.
When I get done, all right. Okay.
We're a little more casual down here. We're just gonna do the best we can on the schedule and not worry about it.
So we need to ask
wanna
other
hear what you
questions.
got to
So how was
say, all of
breakfast?
it. Bring it on.
So that's all the earlier testing. Yes, I just asked because I was expecting to be about 15 minutes in, only half an hour. 18650 testing. This is the stuff I haven't yet sort of reported on for anybody who's been kind of following what we're doing. This is all new stuff. So this is a series of tests using 18650 cells. It's not desperately secret, but I'd be grateful if you would sort of perhaps keep it amongst the community for the time being, because we're we've got some commercial stuff we're doing in relation to this, which I'm going to explain, which you know, we're just trying to stay slightly under the radar at the moment. We've developed, among other things, a slightly different charging algorithm. We've taken out IP protection on that. We don't really, you know, we don't want to sort of, I mean, in a sense, the objective is not to make money out of it. What we want to see is some batteries handled better in a commercial environment. So we've managed, on the basis of the IP, to secure some grant money. So we've put in about 15 grand or so of our own, my brother and I, but we've also got about 10 grand from grant. So that's funded a lot of the stuff that I'm showing here. And we couldn't have done that if we didn't have something that looked like a business plan. And we're kind of hoping to recover at least some of the costs from licensing some of this stuff to big players. So if anybody knows anybody in Tesla who might be good to talk to, because we can't get through we've talked to BMW and Bosch and people like, and Lear and people, we can't get through the crank filter in Tesla. So we'd just like to sort of stay slightly under the radar for the time being. Next few weeks, where my brother and I are hoping to submit a paper to a journal with some of this stuff in, but we may get kicked out. Then these are similar to the types of cells used by Tesla. The sort of mouthful of alphabet soup here, sometimes reduced to NCA, and then the more alphabet soup here. These, I think, are a mixture of lithium, nickel, cobalt, manganese oxide, and lithium manganese oxide. So these are all different chemistries, and really what we were wanting to look at was how you know, whether the results that we'd seen with lithium iron phosphate were applicable on these other cells. So again, we were using 8-cell packs. One of the advantages of 18650 is they're a lot smaller in terms of capacity, obviously. So things like all the electrical hardware and so on was smaller and cheaper. Again, we did the sort of same process as before. We bottom balanced the cells before assembly. We screened them. We bottom balanced the cells and then just left them for a week and monitored the voltage, looking for any that it had any significant self-discharge. And then we cycled the cells and we recorded the voltage, obviously, anode and cathode temperature, or, you know, the can, both ends of the can really, on an 18650. Recorded the temperatures, because one of the things that we're currently still analysing is those data, because we're very interested in the extent to which temperature signatures, if I could put it that way, can be used to work out the behaviour of the battery.
John, excuse me, what the screened part, what did you do as far as?
What we were looking for is cells that had any kind of accelerated self-discharge, because broadly speaking, these cells, the self-discharge is extremely low, but there seems to be a small minority of cells that from the factory have some sort of a problem, where there's an accelerated self-discharge, and it might be a bit of crud that's been built into the battery that's allowing a little bit of charge to leak across from the anode to the cathode, and we just wanted rid of those cells. We didn't want them in the pack. two reasons. One was we didn't want, oh, I've got this thing in my eye. We didn't want the cells in the back because the accelerated self-discharge meant that the cell would go out of balance compared with the others. But the other reason is that if you got that kind of a defect in it, in the cell, then I used to say that the jolly thing isn't going to blow up.
Yeah.
So,
Did you find actual soft shorts in some of the 18650s?
what was very interesting, which I'll come on to, is we didn't find any at all in the 18650s during the screening process. I found two in my 100 amp hour calbs. I had two cells that were, I ordered 38 cells and two of them were had soft shorts. But what's interesting, and we'll come on to it when we get to the cell failures, we actually had a couple of instances where they developed soft shorts during testing. And that was interesting. So here's a sort of, I've acquired myself a brand new garden shed. I'm very proud of it. And this is one corner of the new shed. It was partly paid for by the grant and partly by us. So we've been attempting, not very successfully yet, because of a problem with noise, electrical noise, to provide some sort of a chamber where the temperature can be kept reasonably constant, just so we can control that. But that's basically the setup. And you can see with these little yellow things here, those are each of the individual cells. And then that massive spaghetti was my homework for many happy hours, getting all that not rigged up. So just summarising the results of what we had, the first of these are the lithium cobalt oxide cells. The first one of these, their capacity was nominally 2200 milliamp hours. We got up to cycle 159, and I'll be showing you the graphs from this a bit later. And one cell developed a fault, and it basically clapped out in fewer than 20 cycles. This one more or less ran to completion. I can't remember the exact cycle life on this, but I think it's of the order of 500 cycles, since there's some published cycle life. So we ran that well to completion. The Senyo cells, these are the lithium manganese cells. Again, we ran the cells well past their published cycle life. Panasonic cells, this was interesting. It toddled along quite cheerfully, and then one of the cells started to go bad, and it suddenly went open circuit. And we were taking the voltage readings every 30 seconds, and between one reading that was normal and the next, boom, the cell was open circuit. So that was the end of that test.
Load or charge or spin?
I'm sorry?
What was the activity when that happened?
It was during charge. I'll show you the graph of that later on. But there were a number of issues about that were quite interesting. These are the lithium manganese kitchen sink cells, the Samsungs. This is test 5. About 500, I think it was cycle 499 when I shut it down just before coming. And on cycle 254, which is the last one I measured, it was around 7 millivolts was the difference between the cells. So again, these cells are not drifting. This one is on the stocks. I've partly built I've got all the stuff, partly built the rig. What I'm going to do with these is put 4 of the cells into a chamber that's about 8 degrees centigrade, and then the other 4 into a chamber that's, I don't know, 20 or 30 centigrade, and then just cycle the pack, because one of the things that the all the leather patch brigade, you know, the existing battery experts say, is that one of the reasons for drift is temperature variation across the pack. So I confidently expect that they won't go out of balance, but we want to get the data to try and convince people that that's the case. So that's, did I explain that very well? This last test is cycling with the two halves of the pack at different temperatures. So this is a typical voltage and current trace. There are again 8 cell traces there with the voltage scale here, and you can see that we're going up to 4.2 volts on the scale. And then this is the current. Oops, move the other thing there. Is the light shining on you guys? And you guys at the back? Are you getting a glare on the screen?
You can see it.
Must be a way of doing this.
Are you trying to make it worse?
Let's make it worse. Or we'll just have to live with it then. The red dashed line is current in milliamps. So you can see here, and the 0 there is about there. So what's happening here is we've got roughly minus 2 amps, just over 2 amps. So that's the constant current part of charge. And then the current is tapered here during this phase here, the constant voltage. And then the current drops to 0. So this is a rest period. And then a resistor is switched in, and the voltage drops as the thing discharges. So without now running it roughly 2 amps the other way, and then there's a rest period there. So that's the entire cycle. Oh, I've got one of these gadgets.
Is this 100% charge and discharge, or 80, or?
What we did was, the majority of cycles we were, I mean, you can't be precise because the capacity changes with time, but we were looking for about 70%. But then every 50th cycle, we would actually do a sort of full discharge. We always charged fully, but every 50th cycle we'd do a maximum effort discharge until the weakest cell got down to a voltage. We use that for capacity checking. So just to summarize, this is the sort of constant current part of charge. Now this is the bit that where we've done some tweaking. What we're doing there is that the way the charge is controlled is it's working a bit like constant voltage in a normal single cell charging. But what we're doing is we're looking at across the pack at all the cell voltages, and then tapering the current based on the highest voltage cell. So what should happen is that all the cells go up fairly close to here, but then there'll be one cell, you can just see it, there's one cell that's slightly above the others, and what the electronics are doing is tapering this current to maintain that top cell at the highest voltage. And you'll see the effect of this on some of the, it doesn't make any difference with that pack because it's very well balanced. But if you have any issues with the pack, then it makes a difference. Then we've got a rest period there, then a discharge, and another rest. So are you comfortable with what you're looking at there, or do I need to explain it further? If we take that chart and compare it. This is the lithium. This is a lithium iron phosphate cycle. These have got, broadly speaking, similar type of regimes. The constant voltage in that one is very short, and also it's constant voltage of the whole pack rather than constant current, but it's otherwise the same. It's got the rest and the discharge. The one at the bottom is obviously a maximum effort one. The discharge curve has gone over the knee. So compared with the lithium iron phosphate, the constant current phase is much steeper. You get a much bigger change in voltage between discharged and charged on the other chemistries. Well, all the other chemistries are tested. You get a much steeper charge there, which I actually wonder whether that might be related to why lithium iron phosphate isn't as widely used as you might expect in original equipment cars, because with that much steeper curve you've got a better chance of guessing the state of charge for the voltage.
So you're saying the 650s, you're testing all those chemistries as more of a linear discharge?
Well,
Not so
what I'm
flat.
saying is that there's a much bigger difference in voltage between a discharged cell and a charged cell.
Well, let's go to the other end. I see a pretty linear line here on the discharge.
Yes, but again, there's quite a large difference in voltage between fully charged and fully discharged. So fully charged on this one is about 3.9, 3.4, and then fully discharged is, well, it's not even fully discharged here. It's not over the knee. You know, it's about 3.4. Whereas this one,
It's very flat.
it's much flatter. I mean, ignore that part of the curve.
Right.
That part is really very flat.
There's no forewarning, it's going to drop off.
Well, you can't use voltage as SOC
Yeah.
as much on the.
Yes, exactly. I mean, it's the relationship between state of charge and voltage. It's a bigger factor in the other chemistries than it is in lithium iron phosphate.
But for a car, other than detecting state of charge, I like the flat discharge curve. I
Yes.
get the same consistent performance.
Yes.
Fully charged to the end of charge.
Yes.
Although it does come upon you rather suddenly.
Quickly.
And then the more linear curve, you're going to wind up, with a changing profile in the car as you discharge, but it would be easier to tell where you're at by voltage.
The racket would say, whoops, there it is.
So, a couple of things I'd say about that. One, I really doubt that would be the determining factor in the choice of chemistry. I'd say for an OEM vehicle, it's going to be about energy density and cost and life cycle. But energy density is the number one. They're trying to cram as much battery in as they can per dollar, per weight and volume. And the other thing is, with that such a wide variation in cell voltage with state of charge, what that implies is that there's actually a significant difference between bottom balancing and top balancing. So bottom balancing, you're keeping the cells on average further down that discharge curve. Top balancing, although you can't extract any more amp hours out of the pack because you're limited by the weakest cell, you will have a higher average pack voltage if you top balance, and so you'll get more energy out of the pack by top balancing.
Yes, I see what you're saying is that if you've got a top balance pack,
Yeah.
then on average all the cells are going to get up to 4.2.
Yeah.
So you'll get more energy out.
More energy.
I have seen that suggested in a paper as well. I think it's a fair point, but I think it is a fairly theoretical one. I mean, the actual difference would be quite small.
Obviously, with
And
phosphorus.
let's talk just a little bit the knee on the bottom graph, you still have one on the top, he's just not showing it.
Yeah.
They turn down sharply at some point, but he's doing a 70% discharge.
Yeah. Yes, I mean, I've slightly got apples and oranges here because this is a full discharge and this one's a 70% discharge. So this one has a knee as well, but I've picked a bad example really as a comparison.
But in the mid-range, what we're noting is the LiFo 4s is flatter.
Yeah.
And these are.
So
moving it to the top, you're not, I don't.
not with
think you're
phosphate cells, you're not going to make any difference at all, but with these other chemistries,
gonna- I don't think so.
well, even if it's 10%, that's a
I think the thing is, it wouldn't be as much as 10%. I think you're right, absolutely, and that's good. That's good analysis of the problem. But I think actually the difference would be so small, you might be down to be into the fractions of a percent, probably.
well, it'd be an interesting thing to,
Yes.
John Metrick
measure.
was working on that, and he was making the same argument, but he uses it for one run down the track, and then does that top charge again, because he gets a tiny bit more, but it's for an 1/8 mile.
Yeah.
So how is that going to help you if you're not racing the car?
Yeah, 5 seconds is different.
Well, the effect is you get the same power at a lower current level. And I don't get the
Slightly.
application.
or in John's case, more power.
We get
Yeah,
our,
more current
we get
potential
our
if you
torque
hire
from the
more
current. I want more current, I don't want necessarily more.
Rolling to speed, curve is torque. Ohm's law.
Anyway, that's it. The other observation is that percentage-wise, there seemed to be a slightly smaller drop-off in voltage at the end of charge. The voltage didn't drop off quite so much. But with both of these, do notice that the, particularly at the end of charge here, and you can see it there, that the voltage doesn't just drop off immediately. That you've actually got a sort of dynamic effect with a time constant in it, which means that the voltage decays rather than simply just drops off at the end of charge and the end of discharge. Right, some of the cell failure examples. It's about 10 to 10. We're all right.
We're fine.
Yeah. Well, if anybody wants to break for a coffee and
No.
continue afterwards at any point, just shout. I get the bit between my teeth on this stuff, and I forget that people need the loo and so on.
That's
This-
their problem.
This is. Do you remember I was saying the first set of lithium cobalt cells we had a cell failure which halted the test. This is the voltage and current trace for the last 18 or so cycles before the thing went belly up. And I better point it out rather carefully. This is similar in principle to the graph that you've got before. In other words, that you've seen before, just very much compressed this way. This is one cycle from here over to there, and it's very compressed that way. We've got voltage, as we had before, we've got voltage here, then the red dashed line is current, and the current axis is over here, and then I've stupidly put time along the bottom rather than date, but that's probably over a considerable period of time. I just think a couple of days, possibly. I can't remember the exact number. But you can see if you look at these are 8-cell voltages. So we've got that's the constant current charge. That's the CCV part of charge. Then a rest, and then discharge. And you can see if you look carefully. Can you see here we've got one cell has gone above the others here, and then as we go across here, there's one cell that's more and more of an outlier. By the time we get over here, the cell is not even getting to 4.2, and as soon as we start tapering the current, it drops like a stone, and you can see that it's actually the same cell. There's an outlier here. So basically what was happening was that one cell is simply just no longer holding any kind of charge. And if we blow up the magnification a little bit on the first one, like this, blow up the magnification, this is exactly the same data, except I don't have the current showing. For the first of the cycles, it was on the previous page, and you can see a little more clearly here that we've got one cell has gone up to 4.2 volts. Bearing in mind this is we're using our electronics to taper the current against the voltage of the highest cell. And then we've got the other 7 cells struggling along in its wake. That's a lot to absorb. Do you want me to go back or explain more what you're looking at there?
Well,
We
is
got it.
the one cell that's peaking up also the cell that's joined to the
Yes,
bottom?
it is. Yeah. The one that's, yes, this one down here. You can see it's green there. It's the same cell.
So the cell that's peaking so fast, it's developing a higher internal resistance faster than the ones that are still taking charge.
Well, it's yes. I think this suggests a higher internal impedance, and that it might indeed do that, but I don't know.
Yeah, well,
Could I
yeah.
ask a question, John? How are you doing the terminations to these 18650s?
I started off trying to do it mechanically, but then we ended up with getting tabs put on and soldering them.
Sorry.
Yeah. Because we found that trying to use a non-soldered mechanical connection was not reliable. So these are both the main current carrying path and the voltage measuring circuitry, which is separate, are soldered to tabs which are flash welded to the case.
I get a lot of calls from somebody with a bad cell, and it takes a charge, shoots up in voltage very quickly, and when you put it under load, it drops in voltage very quickly. And we've taken some cells back and replaced them, and there's nothing wrong with the cell. And I've started kind of beating them up on their connection to that cell. Every intern that's ever served at EVTV has brought me a cell and our little bottom balancing device, which brings it down to 2.5 volts, and then releases it, and the voltage goes back up. And at 2.76, it kicks back in. And they brought it to me, and it goes chunk, a chunk, a chunk, a chunk, a chunk, a chunk, and they've got a bad cell. And every time I've tightened the terminals, I've gone away.
Yes. Well, absolutely.
It's like a running joke around here. Everybody brings me this magic bad cell.
Yes.
That when you put it under load, the voltage just drops to nothing.
you have the Rookie Bone Award to give him with that cell.
And I had a guy, a PhD double E, read me his resume over the phone and his CV, and explained to me that he absolutely had a bad cell. And the irony was he was returning it to another supplier. He never bought the cells from me. And he described it to me. I said, "There's nothing wrong with the cell. You have a connection problem." And we had a ferocious argument that ran for a week. And but he was gracious enough that 45 days later he sent me a brief email that maybe that connection was
That was very good of him, I'm glad.
It was nice he closed the loop, because he really made an ass out of it.
We still got class to admit it.
So that was the first of the previous ones. Then you can see on this one that we've got again a higher impedance, but they're staying closer together. But then this one is dropping off during the constant voltage phase, and then it's dropping down below the others. So
Pretty
it's
good
beginning to go bad. And then we've got another one here, the third one along. You can see that it's actually, you know, again, it's the
Getting
voltage
worse.
is going right up here, but then during the current tapering and the rest afterwards, it's dropping off.
John, the cell in the first cycle that hit voltage first,
Yep.
is it the same
Yes.
cell that is now dropping off precipitously?
Precisely. That's the same one as that one and that one. It's all the same cell.
Are these energy losses significant enough that infrared tomography would flag that cell in the process?
That's one of the things we're still working on. We've actually got anode and cathode temperatures along with each of these voltages,
Well,
but we've got so much data we haven't really finished analyzing
those are
it.
direct measurements. What I'm saying is with the really high-end cameras, they'll show you a difference of, you know, 1/100 of a degree C almost,
Yes,
it seems
yes.
like, on their digitized image.
Yes, yes.
What's the relationship to your outlier at rest to the other cells?
I don't know that we. I mean, before the beginning of this, they were all right together. So you know, a few cycles before this, they were fine. And then, you know, obviously, by the time this had finished, the bad cell was toast anyway. There was nothing left to measure.
That's the declaration.
This is again a similar. This is the second set of cells. This one, it's the same cell type as previously, lithium ion cobalt, but it's a fresh set of cells, bottom balance screened and so on. And what we got here is just one cell that has fairly high impedance. I mean, it might be a bad terminal thing, but I don't think so, because as I say, we soldered all the terminals, and it was extremely consistent. It just went like that for 600 cycles. You can see what's happening here is one cell almost immediately goes up to the 4.2 volts, and then during the current tapering phase, the rest of the cells pretty much catch up. But this one is actually dropping on discharge, again because of its impedance. This is a 50th cycle, and you can see that it's gone, the voltage has gone right down. But actually, by the time it gets down to the bottom, with relatively lower current, the difference is getting less. So that's what it looks like with one cell slightly higher impedance than the rest. So we've got one cell slightly higher voltage on charge, lower voltage on discharge. But the test just ran to completion. I mean, it just kept doing that for 600 cycles, and there was no significant change. So it wasn't really a problem. The only thing I would say about this, a simple BMS would have had quite an interesting time with that, because it would have thought, high voltage, this cell is out of balance compared with all the others, let's put some current out of it. The other thing it would have had to have done is stop the charge almost immediately. If you got the simplest form of BMS, which simply looks at the cell voltages and say if one of them is over the limit, then quit. Then the pack would have been practically unusable. So again, this is winding up the magnification on one of the on one of those cycles. You can see we've got the high impedance cell. When the charge starts, it goes up almost immediately to 4.2, and then the rest of the cells effectively get most of their charge during this sort of CCV phase, and then they're pretty much together during the rest, and then this one is lower than the others on discharge. Does that make sense?
And the amount is almost identical on both ends of the curve.
Sorry, in what sense?
The voltage differential between the
Yes.
outlier and
Yes.
the drop on the
It's
other
not,
end.
yes, I haven't actually checked the numbers, but yes, I mean, just visually it does appear to be that. So, I think that, let's just say what I've already talked through. So we've got a one cell high impedance, and the thing is still working right. I mean, for interest, that's the capacity of that particular pack. So what we've got across here is the capacity in milliamp hours of the pack, and then across the bottom here we've got cycle number. So we go up 600, between 600 and 700 cycles. This line here is the sort of theoretical specification. So the spec sheet said this would be the rate at which it would decay, and then the blue line waving around here, probably on temperature as much as anything else, is the actual that we saw in the battery, and then the red dotted line is the trend of the actual stuff. So you can see that what's happened here is that nominally, and it may be just be a matter of instrumentation differences in conditions, we started off rather below the spec capacity, but actually the curve is shallower. So by the time we get out here, we're actually at pretty much the what the cell manufacturer said should be in terms of capacity, and that's with a pack with that one high impedance cell. So even with a high impedance cell, we're getting something that's pretty close to what the manufacturer says should come out of the pack.
John, how far out does the supplier project the cycle life?
It seems to be fairly vague. The spec sheets, they say things like not less than 70% after 500 cycles. They don't appear to say it will be X. You know, you can run for 1,000 cycles without problem. I mean, I just don't know what would happen if you kept going with these. I imagine if you kept cycling long enough, sooner or later something would go wrong with the cells. I don't know.
Looks like the specification projection is trending downwards at a more rapid rate than you're actually seeing.
Precisely.
Which might project that the batteries have more life than the supplier projected.
Yes. I mean, I think the other thing, to be fair, is probably the battery supplier is based its specification on a more vicious discharge regime. I mean, most of the time we're only discharging ours to 70% or something like that, so you would expect them hopefully to last a little bit longer.
Do you see an automated environmental stress screen coming out of this for production?
Sorry, an automated?
Automated environmental stress screening for these lots and batches of batteries using this type of...
I would certainly see some sort of improved procedures, particularly in high value like aerospace. You know, I mean, I think if they'd got any of this kind of level of monitoring on the 767 battery, that it caught it long before it became a problem. 787,
787, yeah.
Yeah, getting confused with my airplane type. Right, the next one. This was the Sanyo one, and this one again. This was just simply our fault. I made a mistake on the wiring, and at one point, or for a period, I had one of the cell voltage connections bypass the voltage followers. So this round to completion. Same thing here, cell voltage up here, 8 cell voltages, current over here, and ought to be date across there rather than time. And you can see that one of the cells is just consistently below the others. both on charge and discharge, but it remains the same. So that's a case of a cell that's just started out of balance, which again it just ran to completion. But if you had that situation and you ran the pack down to the car stop, then you would probably trash that cell. Again, winding up just the level of detail slightly. Here you can see the out of balance cell compared with the others. So this one has gone over the knee, while this one is still, well, the rest of them are still fine. So that one would undoubtedly, in a real world situation, if you tried to fully discharge the battery without voltage, without checking on the cell voltage, you'd end up with the cell being mugged by its contemporaries. This was the Panasonic cell. So this is another kitchen sink cell. This is the NCR18650 Panasonic. There's the one with aluminium and all sorts of other stuff in it. This was the final cycle. It was the start of cycle 319, and it all looked fine. And then suddenly, this is the final reading. And then the reading after that was an abort, because the software detected a problem in the thing, and it just I think I got some crazy reading off the voltage or something, so it said enough of this. So the cell suddenly just went open circuit. If we went back, this was at cycle 150, so that all looks sort of okay, really. We've got the charge, and then the CCV, and then the rest, and then the discharge, and this one looks like it's gone down to about 2.7 or so, and then bounced back after that. I must say I quite like these cells. I can understand why my Tesla used them. They seem to be fairly comfortable about relatively high currents. I say we were temperature monitoring them, and they just didn't seem to notice relatively high charge currents. Whereas with the lithium cobalt, for example, if you tried shoving a high current through them, then they got a bit hot and steamy. Whereas these ones look good from that point of view. But by cycle 300, we've got a couple of outliers. This one here is cell 8, which is the one that eventually went open circuit, and this is cell 1. And it's very strange because you can see that they're not too badly off here, but then they're dropping down a bit here, and they go really quite badly off at that point. So that was about 20 cycles before the failure occurred. What was also interesting was that the temperatures of these cells were they started in the middle of the pack sort of thing in terms of their average temperature, but then the temperature was going way up, relatively, well, way up, you know, a degree or two up. Yes, that's right.
Am I reading this correctly, John, that we have a much lower voltage at the end of the discharge, and at rest it goes to a higher voltage than the other cells? Or a lower voltage?
The bad cell.
Yes.
The bad cell is below the others on the rest as well. What we surmise is happening here is that we've got a combination of two things. That we've actually got a bit of self-discharge in those two cells. Cell 8, the one that went open circuit, was worst. Then we've got some self-discharge there, which is why this is beginning to go over the knee while these are still fine. But the other thing that we suspect that we might have is relatively high internal impedance. And there are two reasons for that. One is you can see that they're fairly close together here, but there's a wide variation there. So what we suspect is happening is that the high impedance combined with the lower state of charge is about the same voltage on charge, but then on discharge, the difference in state of charge and the impedance are both working in the same direction, so the voltage is a lot lower. And as I say, the other reasons for suspecting a high internal impedance is the cell temperature. So I kind of is fortunate that we didn't end up with anything more awkward than simply the cell going open circuit, because it's got some combination of self-discharge and high impedance. Who knows what's going on inside the cell? So
What temperature did that cell go to that had high impedance?
it was relatively small amount. I think the whole temperature range was of the order of maybe 10 degrees above ambient, 10, 15 degrees above ambient. So I think probably, I'm doing this from memory, so don't quote me, but I would think probably what happened for that cell that failed was that it went up from somewhere around the average for with its contemporaries, up maybe 2 degrees, something like that.
C you're at.
Sorry?
C Celsius.
Sorry, centigrade, yes.
Okay.
Sorry, beg your pardon.
John, for the cells that did go open circuit, is there any protection built into these 18650s?
Not unless they've messed me about. The supplier, I got these cells from a fairly reputable supplier, and that was one of the things that I checked.
It seems to me like if there was a protection circuit, that going open circuit would be a safe failure.
Yes, true. Yes, I think a protection circuit would mess us about beyond all recognition. That's it.
Well, some capacitors are built that way. They've got an internal fuse, but they've never done it with the 18650
Yes.
yet that I know of.
Yes, I suspect that this was an informal fuse.
I read that Panasonic had something with the separator or something, that they did have what you would call an internal fuse.
Emergency foil leaf in there, built and fail, mechanical fuse, thermal fuse.
But I mean, you can see that the current wasn't that excessive anyway, neither was the voltage. So it was just chundering along quite cheerfully. It should have been all right. They'd done it 300 times before. So, right, so there's just a few examples of cell failures. Self-discharge. One of the other things that's I think probably people are gradually coming around to the view that these cells don't self-discharge very much. I have no explanation really for what's going on here. Let me try and explain. What we did is at the end of the test, this is the set 2 test. You saw one of the graphs earlier. This is the second set of lithium cobalt, not the set that had the cell that went completely bad. This is the other one. What we did here was we set the pack on one side after it had been after the test had finished, and then every week I went out to the garage with and got a 5-digit bench voltmeter again paid for by the European Union, and measured the cell voltage. I would say I'm being a little pedantic because this entire vertical scale is only 50 millivolts, but that's the trace of the cell voltages. That's showing the cell voltages recovering after the last discharge on the test. But the thing to notice here is that that's the end of June, and that's the middle of September. So in other words, they've recovered not a lot, but a little bit, and they're still recovering 2.5 months after the cell went open circuit. That is seriously odd, and I have no explanation for it at all. I suspect some of this stuff in the middle was probably I was measuring the temperature on a warm or a cold day, but you can, the fact that they all went up together suggests that it wasn't actually just my getting my numbers muddled up. It was very strange.
You have convergence obvious without temperature being a big factor. You can see.
Sorry, say again?
You could have calendar date variations due to temperature, but you've got convergence over a wide range.
Yes, yes. The other thing that's interesting about this is if you're using open circuit voltage, as is fair to do if you leave it long enough, open circuit voltage as some sort of a surrogate for balance. These are only 5 millivolts or so spread across all those cells, which is not a very great deal of spread of them. These cells have not been balanced since before the test started. So I balanced the pack, cycled them for 600 volt cycles, and then just let them sit. So, and 2.5 months after the end of the test, they're 5 millivolts apart. The other slightly curious thing about this is they should have been decaying. You're supposed to have a self-discharge on these cells. The spec sheet says 1 to 3% a month, and that's not what I would call. It doesn't jump out at you, you might say, from that.
Let me offer a couple of thoughts here.
Sorry?
Again, everyone in the battery industry, including the manufacturers, believe in self-discharge. I can't find any here. I can't find any anywhere. It's not that I question their authority, but it's shown me where this is.
Yeah.
My mental picture of this, there's no mystery here. And it has to do, all of them having a graphite anode, with my nightclub theory. And these are just lithium ions. We're not putting any more in the anode. We're not taking any more out. But they space themselves. And they like to be every other hexagonal cell in the crystal matrix. Now they'll sit next to each other, but they would rather be every other one. And then there is kind of my picture of the layers is a little oversimplified from what happens. There's a A, B, B, A, B, a layer structure that's a little more complicated than every layer being identical. And so I'm kind of, as the other guys with the BMSs were always going and talking about internal resistance as some sort of magic word. My magic word is diffusion.
Yes.
And I attribute a lot of things to diffusion. And here you got 2 months of cells at rest. We're not putting any current in. We're not taking any current out. But the voltages are converging. And this is simply cations, lithium ions, in the anode, gradually sorting themselves out to find the optimum distance between each other in the crystal labs. And as they get sorted out better over time, that voltage would naturally converge. So this would be right off of my mental image of diffusion of some batteries that are just sitting there at rest.
I absolutely agree. I think the thing that surprised me was the length of time. I mean, the sort of diffusion that I've seen before on when you're balancing batteries, you know, after 3 or 4 days, they're sorting themselves out. So this was really
3.65 to 3.685.
Yes, it's not a big.
This is blown up pretty big.
It is, yeah, 50 millivolts top
Right.
to bottom. It's not big. You know, you wouldn't detect it using.
You wouldn't see it at all if you weren't looking at that.
If you didn't have a Grant meter, you couldn't detect it.
Yeah.
And so that's like the definition of entropy.
Yeah.
Almost, to
That's
me.
what I was thinking.
The other one was much more sensible. This is, again, the post-test voltages. We've got one outlier here, and I can't off the top of my head remember what the provenance of that one is, but all the other 7, I mean, at this level, and again, we're not talking about a huge range here. This graph is more compressed this way, but there is a slight drop in voltage there on this one. So these cells, if you use a lot more powerful enough magnifying glass, you can actually detect a little self-discharge on these cells, but it is very small. I've been boring you guys for nearly an hour and a half. Should we take a potty stop? And if you want more of this when you get back, what do you think, Jack?
Yeah, let's just wrap it up. We do have some other sections we can get in this morning, John. Is there anything from civic test bed and plans that they want to add?
I don't think so. Not that's critical now.
Okay.
I mean, that I've done all the probably the most interesting battery stuff, really.
Very good. I want to thank you. It was a fascinating presentation, and I love this. I'd offer a couple of things. We have some OEM battery packs in here. I'll take a look at them. There's some Tesla modules. There's the Better Place packs and so forth, and so these use different forms. As John acknowledges, these are people going for the ultimate in energy density, and by that the most capacity for weight and volume. The lithium iron phosphates simply do not meet their criteria. And we're in a plastic case with 2 terminals that you can drop kick across the room and you can't really hurt them. Now, after selecting these supercells with much higher energy density, take a look at all the shit they put around them to be able to use them at all. And they give it right back in weight and volume, in hardware and EMS stuff and structure and so forth.
Cooling system.
You guys are used to making a lightweight .090 aluminum box, dumping the cells in them and strapping them up. And if you take the volumetric and gravimetric density of what you're doing and what they're doing, they beat you by 0.001% or something stupid. It's so don't, because they're OEMs and very educated people, do not assume that they've got you licked on any of this, because it doesn't work out that way. Sir?
In the future, do you see the lithium iron phosphates being similar in price to the?
They're already lower price. But even the Chinese battery manufacturers are going to these chemistries. I don't think it's going to matter. 2 years from now, I don't think any of you will be using Chinese batteries except in your existing cars, because I think the availability of Nissan Leaf batteries and Chevy Volt batteries and Tesla batteries is going to be such. I'm getting weekly offers for Tesla drive units and batteries at ever lower prices now. The salvage market's kind of already got all the low-hanging fruit, and they're down to me. And my ability to buy this shit is somewhat limited too. And so it's just too easy to wreck a car and too hard for me to pay for the parts, and for everybody else. So we've got a deteriorating price structure on salvage parts that's going to work to your advantage very well. You're not going to be able to afford the Chinese batteries, not because they're terribly expensive, but because the Nissan Leaf and Chevy Volt and Tesla modules are going to be so cheap. We're at kind of the end of the importation of Chinese lithium iron phosphate cells and are the victim of whatever choices the OEM made. I don't agree with all the choices, but we're taking all that stuff off. I have to say that I'm getting where I kind of like these cells, like John was saying. The Better Place battery pack out there, in another one of my Alzheimer senior moments, and some employees who rewired something for me while I wasn't here, and no one's ever been able to explain who or why. That Better Place pack out there, I took down to 45 volts. It's never been bottom balanced, and I put 65 amp hours in it, in charging it exactly to 400 volts. I didn't. So I can't tell it was damaged.
That was a 90% plus discharge, wasn't it?
It was 110%. But the yeah, I put 65 amp hours into a 65 amp hour pack and was back up at the top. Now I haven't tested it for maximum current output or anything like that, but I can't find any damage in capacity there. And for these cells to be at 45 volts on 96 cells is a half a volt per cell. This is egregious damage, and they weren't bottom balanced. Now, they did discharge at a very low current rate. What I'd offer to John, I'm very excited about what you're doing, because you're assembling some tools here and a process that you could do something that most people can't do. And it's kind of the holy grail for me. I've always thought if I read messages from God in cloud formations long enough and watched enough paint dry and enough grass grow, that I could discern and develop a test methodology where I could take a cell and run it through a one-day test and tell you how long it will last. There is a guy who, I can't remember the university or the guy's name. Tesla has now funded him, by the way, and we talked about him.
Don, in Canada?
Yes, Nova Scotia or something.
Fairfax.
Halifax or Fairfax University.
Dalhousie.
Dalhousie, that's right. And Tesla now has funded his program. And what he's doing is measuring very accurately the round trip efficiency of the charge cycle. In other words, if I take 100 amp hours out, what do I have to put back in to get back to the same state's charge? And is that a 96% efficiency or 98% efficiency? And using that to predict cell life, basically. And so that's an example of something that could be. But keep a sharp eye out while you're doing this. You're getting enough different things you're measuring here at a scale that's happening rapid enough that something might jump out. And that would be a very marketable procedure if you can figure out how to put a cell on a test stand and tell you how long it's gonna last. That would be cool. Great presentation, John.